Welcome to today's Explainer. We're jumping right into a fascinating topic, the quadrilateral family tree. So buckle up, because we're about to decode the literal DNA of four-sided shapes.
We see closed, four-sided shapes everywhere, right? But beneath their simple exteriors, there's actually a pretty wild genetic code. To kick things off, let's chew on this classic geometry riddle. Tell me, if every square is a rectangle, is every rectangle a square? It's one of those questions that trips up a ton of students. But I promise you, by the end of this explainer, you won't just know the answer. You'll deeply understand the strict hierarchy of shape properties that makes it true. It's all about what traits a shape inherits and, well, what traits it doesn't.
Okay, let's dive right into this map of our shape family tree. Think of special parallelograms as our big, overarching family bubble. Inside, we have the rhombus hanging out on one side, the rectangle on the other, and sitting right there in the overlapping middle, the square. This beautifully sets up our family tree, starting with the absolute parent of them all, the parallelogram.
So let's get our foundational shape clearly defined. What is a parallelogram? Well, it's quite simply a quadrilateral where both pairs of opposite sides are parallel. That's the baseline requirement, the absolute must-have. It's the general form that all our main sibling shapes are going to derive their base characteristics from. If a shape doesn't have two pairs of parallel sides, sorry, it cannot enter this specific branch of the family tree. But hey, parallel sides aren't the only thing going on here. Let's look at the hidden skeleton of the parallelogram. Because those opposite sides are parallel, they also end up being completely equal in length. The opposite interior angles, perfectly equal too. And here's an absolutely crucial point we're going to come back to, the diagonals. If you draw lines connecting the opposite corners, those diagonals bisect each other. That means they cut each other perfectly in half.
All right, let's branch out to the first sibling in our shape family, the rectangle. A defining geometric law states that if a parallelogram is a rectangle, then its diagonals are congruent. This brilliantly illustrates how the rectangle inherits from the parent shape, but then it evolves. It takes the parallel sides of the parallelogram, sure, but then it straightens the whole shebang up by adding perfect 90-degree right angles at every single corner.
So, summarizing the rectangle's unique traits, all four interior angles are exactly 90 degrees, and because of those perfectly square corners, the diagonals stretching across the shape are completely congruent, meaning they are exactly the same length. Think of it like a perfectly balanced internal frame. Now here's the catch. While those diagonals are equal and they do bisect each other, they absolutely do not cross at 90-degree angles.
Now let's meet the other sibling, the rhombus. I actually like to jokingly call the rhombus a tilted square. You see, if the rectangle chose perfect right angles, the rhombus went in a completely different direction and chose perfect side lengths. Because of this structural choice, its diagonals become strictly perpendicular, and each diagonal perfectly bisects a pair of opposite corner angles.
Let's unpack the magic of those rhombus diagonals for a second. Because all four sides of a rhombus are strictly equal in length, it forces its internal skeleton to behave very differently than a rectangle's. Those crossing diagonals meet perfectly at a 90-degree right angle right in the center. Plus, as those diagonals reach the corners, they slice the interior angles right down the middle. They bisect them. That is a superpower the standard rectangle just does not have. Now, what's really interesting about this is the direct contrast between these two sibling shapes. It's honestly the best way to remember them. For a rectangle, the diagonals are equal in length, but they cross at random angles. For a rhombus, the diagonals are not equal in length, actually one is usually way longer than the other, but they cross at exactly 90 degrees and they slice those corner angles perfectly in half. They are literal geometric opposites in their internal structure.
And that brings us to the golden child of the family, the square. Resting perfectly in the center of our concept map, it draws traits from both the rhombus and the rectangle. It really is the ultimate intersection of properties. I mean, the square is quite frankly an overachiever. It's a regular quadrilateral, meaning it demands complete and total symmetry. It inherits every single trait from both the rectangle and the rhombus. It has four equal sides, just like a rhombus, and four 90-degree angles, just like a rectangle. And its diagonals, get this, they're equal in length, and they intersect at 90 degrees, and they bisect the corner angles into perfect 45-degree slices. It is literally the only shape that does it all.
Now, let's step slightly outside that immediate special parallelogram family for a moment and introduce a distant cousin. Meet the kite. A kite is defined as a quadrilateral with two distinct pairs of adjacent sides that are equal in length. Notice I said adjacent there, meaning sides next to each other, not opposite sides.
Because its opposite sides aren't parallel, a kite totally breaks the traditional parallelogram rules. It only has one line of symmetry down the middle, rather than the multiple lines we see in rectangles and squares. But here is the really cool part. Despite lacking those parallel sides, its crossing diagonals still magically form a perfect 90-degree perpendicular intersection, exactly like a rhombus. It maintains its own beautiful, very specific kind of symmetry.
Let's bring it all together now. When we summarize these traits, just notice how the square checks almost every single box. Equal sides, parallel sides, right angles, and diagonals bisecting at 90 degrees. Then look at how the rectangle and rhombus trade off properties. One gets the right angles, the other gets the equal sides. And way down at the bottom, the kite sits there with absolutely no parallel sides and no right angles, yet it still plays a super vital role in the quadrilateral family.
All right, so what does this all mean in the real world? Let's transition into practical application, because knowing these structural properties actually unlocks some pretty complex algebraic puzzles. Take this scenario. We have a rectangle, LMNO. We're given the algebraic expressions for the lengths of its two diagonals. Ln is 4x minus 17, and MO is 2x plus 13. So how do we find the actual length?
Well, we solve this by immediately applying the exact geometrical rule we just learned. Step 1, we know the shape is a rectangle, right? So its diagonals absolutely must be exactly equal or congruent. Step 2, that lets us build our equation. We literally just set the two expressions equal to each other. 4x minus 17 equals 2x plus 13. Step 3, we solve for x. Subtract 2x from both sides, add 17 to both sides, and boom, we get 2x equals 30, so x equals 15. Finally, we plug that 15 back into our original equation, and we find the diagonal length is exactly 43. See? The geometry is what makes the algebra possible.
Now let's look at a really common pitfall. Imagine someone is trying to find the value of x for rectangle DEFG. They see the corner angle is split into two parts, 9x minus 6 and 2x plus 8. So they do what seems logical and set them equal to each other. 2x plus 8 equals 9x minus 6. But hold on, this is completely wrong.
So the crucial point here is, why is it wrong? Why must 9x minus 6 and 2x plus 8 add up to 90 degrees instead of equaling each other? Well, think back to our family tree. This student mistakenly assumed a rectangle's diagonal bisects its corner angles, making the two halves equal. But as we learned, only a rhombus or a square does that. In a rectangle, the corner is a strict 90 degrees, and the diagonal just cuts through it unevenly. Therefore, the two pieces have to add up to 90. Understanding the why behind these properties is the true key to geometry. And it's the exact same logic architects use to ensure structural integrity and balance in the buildings we live and work in every single day. So I'll leave you with this. Next time you look at a window or see a kite flying in the sky, what invisible lines of symmetry and structural secrets are hiding right there in front of your eyes? Thanks so much for joining me on this explainer. Keep learning and keep looking closely at the shapes around you.